session is opened by Professor Takao Fuji.
Recording in progress.
Okay. The first talk is by Professor Takao Fuji from Toyota Technological Institute in Nagoya, Japan, and he will be talking about mean infrared optical parametric amplifier. Okay, please.
Thank you very much for the introduction. I'm Takao Fuji of Toyota Technological Institute. Today, I'm going to talk about the development of ultra-broadband mid-infrared OPA driven by femtosecond sodium YAP regenerative amplifier. Okay, I think the audience knows the motivations for the development of a coherent broadband mid-infrared light source. For something like 20 years, it has been developed intensively for attosecond pulse generation or advanced molecular spectroscopy. Since good laser materials are not available in the mid-infrared region, it's very common that mid-infrared pulses are generated by using wavelength conversion. When we use ytterbium or Ti-sapphire laser, the wavelength of the pump pulse is too far from the mid-infrared region. Therefore, it is usually converted to slightly longer wavelengths and generate mid-infrared pulses. This is a common technology. But if we have a good 2-micron femtosecond laser, in this case, we can directly convert the wavelengths to mid-infrared, and we can expect higher conversion efficiency and simpler system than using ytterbium or Ti-sapphire lasers. Well, for last decade, various 2-micron lasers have been developed. I listed up these lasers. The chromium zinc selenide, which can provide a very short pulse and also large emission cross section, but it has a short lifetime, 6 microseconds. This is similar to Ti-sapphire laser. Then you need a high quality pump laser for having high energy pulse to have a millijoule output. So in this case, you need polonium yak laser pumps, which is under development, I think. And also polonium yak and polonium EF can generate a short pulse directly, and it has large emission cross section. But the pulse duration is not really shorter than picosecond. It has narrow gain bandwidth. Then also you need to pump the polonium using sodium fiber laser. Sodium fiber laser recently even commercialized the high energy fiber laser system, and high average power, and you can pump with a laser diode. But to have very high energy, you need to very carefully designed system like large core rod for active medium. So the sodium YAP actually can provide femtosecond pulses less than 400 femtosecond, and you can pump with laser diode. But relatively smaller emission cross section. This is some issue of this laser, but we choose this laser medium and built regenerative amplifier using this active medium. Now I would like to discuss how the OPA pumped by 2-micron lasers. In particular, polonium lasers have been developed by many research groups recently and already applied for mid-infrared generation. Polonium has a high emission cross section, and then it's rather easy to extract high energy. There are many publications, but I just would like to show one of the recent publications about such mid-infrared OPA. Pulses from the polonium laser picoseconds, then it is difficult to generate white light. Therefore, they have to use different oscillator from polonium. Here it's polonium zinc selenide, and then it seeds the amplifier. I mean the regenerative amplifier, and also seeding OPA. The system becomes rather complex. So this is a schematic conceptual diagram of a typical mid-infrared OPA based on polonium lasers. The seed oscillator, as I explained, is usually not polonium based, but something else because it's difficult to model and generate femtosecond or generate femtosecond pulses with polonium. For example, polonium zinc selenide or slim fiber oscillator, or even sometimes OPA was used for seeding polonium regenerative amplifier. The beam is split into two, and one is used for seeding polonium amplifier, and the other beam is sometimes amplified and used for white light generation and sent to OPA together with the pump pulse. In this case, the path from the point where the beam is split to the OPA is very long, and the system becomes rather large. We have to worry about the stability of the delay between the pump and seed pulses. The difficulty comes from the narrow emission boundaries of polonium. On the other hand, slim lasers can generate femtosecond pulses. Then it is possible to generate white light directly. Then, therefore, the system becomes more compact, and we can expect a more stable system. This is the motivation for development of OPA pumped by slim amplifier. Actually, a few years ago, we developed such a slim YAP amplifier And the system started from a seed oscillator, from a 3M Zebra mode-locked oscillator, and it was stretched with a multiness stretcher and amplified with a 3M Zebra fiber amplifier. Then after reducing the repetition rate, then sent to regenerative amplifier and amplified up to 1.4 millijoule and compressed with a Tracy compressor. And this is the SHG flock trace of the amplifier output. And the pulse duration was 360 femtosecond. The pulse energy was 1 millijoule with 45 round trips. We tried to build OPA with the laser, but we have found a problem. This is actually is a retrieved spectrum of the white light for seeding the OPA using the flock measurement, and we found that the spectrum was strongly modulated, which means that the white light was not stable. And by reducing the round trip from 45 to 40 and 35, and we see the modulation disappear. And then we think that the white light becomes more stable with lower repetition rate, lower round trips. But in this case, the pulse energy became much smaller. I mean, the amplified amplifier output. Then we need to reduce the round trip with keeping the output of the pulse energy. And we just add another preamplifier, the 3M Zebra fiber amplifier, and then we are able to generate the same energy, 1.4 millijoule, with fewer round trips. Now I would like to explain the detail of the current system of the slim YAP system. Then this is a schematic of a ring cavity oscillator, and the active medium is slim Zebra double clot fiber. The intracavity dispersion is controlled by the multiness stretcher inside the cavity. It is mode-locked with nonlinear polarization rotation. And the spectrum is shown here, and the transform limited pulse duration is 109 femtosecond. The output of the oscillator here is sent to multiness stretcher based on transmission grating. And the pulse was stretched to about 140 picosecond and sent to two-stage fiber preamplifier. The first stage, it is amplified up to 2.2 watt and to reduce the repetition rate down to 100 kilohertz here. And then the final output of the preamplifier is 0.15 watt at 100 kilohertz. The spectrum is shown in this figure. And the long wavelength components of the oscillator disappeared due to the low gain in the long wavelength region. So this is the detailed schematic of the regenerative amplifier ring cavity. The concentration of the active medium, I mean the helium YAP crystal is 4 atomic %, and the temperature is cooled down to minus 20 degrees. The cavity is purged with nitrogen. And the spectrum is, this is the output spectrum, and this is broad enough for 200 femtosecond pulse duration. The spectrum becomes significantly narrower due to the gain narrowing effect inside this regenerative amplifier. And this is the build-up, the pulse inside the cavity, and we get 1.4 millijoule output with 25 round trips. Previously, we needed 45 round trips, and we were able to reduce the round trips by 20. The beam profile is fine here for OPA pumping. And this is the SHG frog trace. And we see a lot of satellite pulses due to the absorption of the residual water vapor inside the cavity. And this is a retrieved frog trace, and these fine structures were retrieved. We used a BBO crystal. The thickness is 0.1 millimeter. And we record the 1,000 times 1,000 trace, and the error of the frog was 0.4 or 3%. And now we compare the trace with the previous one. This is yes, the single stage preamplifier case. We can see the intensity of the satellite is 1 order of magnitude smaller than the previous one. Maybe this is the peaks are basically in blue, and these are red, which is 1 order of magnitude smaller. So actually, the noise level of this trace is larger than this previous measurement, but this is just due to the spectrometer difference. Okay, and this is a retrieved temporal profile and power spectrum and spectral phase. The pulse duration was 265 femtosecond, which corresponds to 4 gigawatt peak power. And the previous system, we had 360 femtosecond and 2 gigawatt peak power. So we improved roughly twice peak power, and pulse duration is much shorter than before. Okay, we used this pump source for collinear mid-infrared OPA. We built I mean, the pulse is split into 2, and one pulse around 1 milliwatt peak power was focused into polarization maintained Zebran fiber and generate white light. The spectrum of the white light is shown in this figure. I mean, this black line. And the spectrum spread from 2.5 micron to 4 micron, corresponds to 4,000 wave number to 2,500 wave numbers. And the other beam overlapped together with the white light and focused into gallium selenide crystal. The gallium selenide has a very broadband phase matching condition in this wavelength range and amplified almost all the white light. Then this is the amplified spectrum. So this brown shaded line, and there's some structure, fine structure here due to the absorption in air, and the idler spectrum also shown here as yellow or shaded line, and also mirror symmetry, on which is due to the OPA amplification. The amplification ratio is about 1,000, and the power of the output was about 10 milliwatt at 240 milliwatt pumping. The beam profile of the idler is shown here, and it is fine for further applications. Okay. In summary, we built millijoule femtosecond pulse generation from stream-based region, and we got much higher contrast than before, and we used the amplifier to pump the mid-infrared OPA with collinear geometry. We got ultra broadband signal and idler spectrum. In the future, we would like to improve the region with gain narrowing compensation and design a region cavity for high energy output. We try to compress the pulse using a piece of IR crystal. I don't believe that the gallium selenide crystal is optimal for the mid-infrared OPA. I would like to try some different crystals. This work has been published in Optics Express. I would like to acknowledge one of my colleagues, Seidari Eswani. Right now, he left our group and working in the company. And also Kazuhiko Ogawa of Fiber Labs. He provided polarization maintained Zebra fiber for white light generation. And this work is funded by this funding agency. Okay, that's it. That's all what I have to say. Okay, thank you very much for your kind attention.
Thank you very much, Professor Fujii. It's very interesting talk and very impressive results. We have time for a few questions, so you can send them to chat box or use your microphones if it's available. Okay. So how can I? Okay, let's go
so
ahead.
I have a quick question. Your preamplifier, where you get about 0.15 watts, it has a lot of modulation in it. It looks like it's too fine to be just from the air and the absorption. So this is between 19 and 1950. Yeah. So where is all that coming from?
And you mean in this one?
Yes.
Preamplify output. Okay. Yeah, I think it's in air. Not in zebra fibers. We believe. But and these yeah, okay. So we believe that this comes from water vapor, but you think this is too fine for the water vapor?
Yeah, I was just speculating. If it is from water vapor, then obviously that's easy to test because you can always add more, you know. But yeah, I was just wondering if you had an idea where that was coming from. That looks better.
Okay, yeah. This oscillator looks more, I would say, water vapor, right? These lines are rather obvious, but yeah, I understand these fine structures. Yeah, might be due to the multimode excitation inside the fiber. I mean the sodium zebra fiber, and this is core diameter is rather large, and then we need to be careful. Yeah, actually, we also checked. I mean the spectrum, and even sometimes it becomes more complex shape, and we have to bend the fiber to have a reasonable structure of the spectrum.
Thank you.
Yeah. Okay.
Okay. Any more questions? I have a few minutes. Okay, if no more questions, please let's thank the speaker again. And now we change over to another speaker. Please let me. Okay.
Okay, thank you very much. I'll stop sharing.
If you just stop sharing, then we can proceed with the next speaker. The next speaker is Vasily Strelkov from Prokhorov Institute in Moscow. And today he will be talking about resonant HHG process and at the second pulse production. Okay, thank you.
Hello, dear colleagues. Can you hear me? Is it okay?
Yes, we can hear you.
Yes, great.
Okay, nice. So thank you very much. And first of all, I would like to thank the organizers for inviting me to present here our results. I would like to present results on resonant high order harmonic generation and at the second pulse production. This project is done in collaboration with Margarita Khakhlova, who is now in King's College London.
Could be changed to slideshow.
I think I'm in slideshow mode.
No, we can see your PowerPoint. There is a mushroom-like symbol down somewhere, and you have
yes, and I press it. Is it okay now?
No, we can still see your PowerPoint. Don't worry, we have a few minutes left from the previous talk. You just take your time and do things properly because this talk is recorded, so it will be better.
Maybe you share your second screen.
Okay. Is it better now? No. Is it better now?
No, it's the same, but probably we should go as it is.
Mm-hmm. Okay.
But
so
you could unplug your second monitor. Then it should probably
Well, I have yet unplugged it. So one more attempt. No. Does it work now?
No, we don't see anything.
Not yet. Not yet.
It was not a good idea.
Василий, в показ слайдов зайдите. Sorry for my Russian. В PowerPoint попробуйте поменять настройки. Там есть настройки показа презентации, где написано...
Да, конечно. Конечно, я это и пытаюсь сделать. Просто я не понимаю, почему. Ага.
Ну, пока вы пытаетесь, мы экран не видим, поэтому...
Okay, so now it says me that my demonstration is stopped.
Okay, let's just go as it is, and I think it's best we can do, and probably
Okay,
that will be enough.
So can you now see my demonstration even in the? Can you
we
see?
can still see the frame of PowerPoint, but we probably have to proceed. Okay. Otherwise we wouldn't have enough time.
Sorry for this. So I'll start my presentation from some experimental results on resonant high harmonic generation. Then I'll present our model of the process and the theory based on this model. Then I'll say a few words about numerical simulations of this process and present results on attosecond pulses generation, where resonant harmonic generation, and also on the role of the dark outer ionizing states in resonant harmonic generation. And finally, I'll conclude. The most striking features of the resonances was demonstrated in experiments on resonant harmonic generation in plasma plumes. So the pioneer results in this field were obtained by Rashid Ghaniev, and here is a reference to one of his reviews. In these experiments, the heating prepulse is focused at the surface of the solid target and provides plasma plume, and then main short intense pulse generates XUV in this laser plume. Here I present as an example recent experimental results on resonant harmonic generation in gallium plasma. So in gallium, we have a bound state which excitation energy is above the ionization threshold.
Vasily, your slide is not progressing. We can only see the first slide. We only see the first slide and nothing else.
Okay.
Can you flip through your presentation? Okay, so if we have this technical problem, can we just switch the speakers? If we can ask Hongcheng Ni to present, and in the meantime, Vasily can fix his presentation, would it be okay? Vasily, is it giving
yes, certainly. Well, just give me the
okay,
last,
so it will give some breathing space, and please let me just welcome Hongcheng Ni from East China Normal University in Shanghai, and he will be talking about quasi-photon at the subcycle level and strong field ionization.
Okay, thank you. But before that, could Vasily quit the screen sharing?
Vasily, can you just turn off your screen sharing?
Yes.
Okay, and now Hongcheng, can you just turn on yours?
Okay, share screen. Can you see it?
Yeah. And can you just turn on your presentation?
Okay.
This mushroom symbol at the bottom.
Okay. Okay, thank you for your kind introduction. And I would like to thank the conference organizers for the kind invitation for giving us the opportunity to present our recent work here.
But
so
can you please start your presentation?
Oh, really? I didn't start it?
Yeah. No, I can see it, but we have the frame, the PowerPoint. It's the same problem with click on the mushroom sign and
let me see. Is better now?
No. Do you perhaps have two screens and you are sharing the not the presentation screen?
That's right. I think it's this case. Is it better now?
Okay, no, it's okay, but can you flip from your slide? Can you switch to the second slide and can you progress through your talk?
Now you're in the presentation.
Okay, that's what we want. Okay, go ahead.
Okay. Yeah, sorry about that. So thank you. Thanks again for the kind introduction. And I'm Hongcheng Ni from East China Normal University. And I will talk about quasi-photons at the subcycle level. So what do I mean by quasi-photon? I would like to start from the light, the concept of light. So as everyone knows, light is can be considered as particle or wave. So in terms of particles, it is composed of light quantas called photons. And in terms of waves, it's described as electromagnetic wave. So it's both a particle and wave because the photon is a frequency domain description of light, and electromagnetic wave is a time domain description of light. And in the frequency domain, in our strong field ionization, it is manifested as multi-photon ionization because here light quantas are absorbed. While in the time domain, it is corresponding to the tonal ionization. And here, this classical electric field suppresses the Coulomb potential from one side and result in tonal ionization. Now, if you consider the light as in the time frequency phase space, it is like this distribution. And the uncertainty relation across this phase space dictates that if you want to define the concept of photon, then this concept would not be valid at the subcycle level. Because if you want to have a well-defined frequency, then the time span must be large. And there's so that you cannot just say at this time there is the photon, because if there is a sharp time distribution, then the frequency distribution will be very large. So there is no photon at subcycle level. And how do we describe the light? As we know, we can either describe it in a quantized signal quantization like this, or in a classical way as a function of time and space. And because in our strong field ionization, the light pulse is composed of a lot of photons. So even if a few photons are absorbed, the quantum state of light is largely unperturbed. So that's why people usually stick to the classical description of light instead of going to the more cumbersome second quantization scheme. Now, if you use a classical field, can we describe photonic effects? Fortunately, the photonic features still emerge. Like if you, for example, in the above threshold ionization, we can still see prominent discrete energy peaks in the above threshold energy spectrum, even if the laser field is described in the classical optical field. So the question now is, where does the photon come from? How does it emerge? As a lot of you already know, the energy peaks can be considered as arriving from intercycle interferences. And maybe an alternative way to present, to interpret this is through the Floquet theory. And by looking at this time periodic Hamiltonian, the TDSE can be right at this. And we define this Floquet Hamiltonian and accompanying Floquet state by getting this Floquet energy out. Now the Floquet equation becomes a time-independent one, and the solution to this Floquet equation is this: if this E and phi is a solution to the Floquet equation, then this E prime and phi prime is also a solution to the Floquet equation, and that's exactly where photons emerge, because these are energy peaks separated by integer numbers of photon frequencies. And now we want to ask another question. Do we really have to do the time translation by an entire cycle? Interestingly, for a system with dynamic symmetry, you don't have to do this. For example, in this Hamiltonian, in this sinusoidal laser potential, you can do the time translation by half a period of the optical cycle. And at the same time, you do a space inversion. And then the Hamiltonian comes back to itself, because it's simply invariant under a space inversion operation plus a time translation operation. And by this, Professor Moiseyev has already showed that by this consideration, one can obtain the selection rules for HHG or harmonic orders. So now you can see that the Floquet theory, if you consider the dynamic symmetry of the system together with it, it will give rise to selection rules. Now we want to go a step further and ask, do we really have to go for at least half a period? The answer is no. If you consider circular polarization, you don't even have to go half period. You can go, you can do the time translation by an arbitrary amount, as long as you accompany it with a rotation operation by a corresponding angle. So you can see that the combined operation is this from this point to this. And you can see that the Hamiltonian is invariant by a combination of the rotation and time translation operation. And this time translation is by an arbitrary amount. So this means there are such dynamic symmetry even under an optical cycle. And this points to the possibility that we can define some sort of quasi-photon even down to the sub-cycle level. And this is ensured by this infinite order dynamic symmetry. Again, the dynamic symmetry contains a rotation and a time translation. And this time translation, the conjugate variable to the time is the energy, and the conjugate variable to the rotation, the angle is the angular momentum. So in order to confirm the existence of some sort of quasi-photon at sub-cycle level, we should look at some correlated spectrum of angular momentum and energy. And we use the acronym of SAME. Okay, then let's look at this same diagram. Here you go. Then this is the x-axis is the angular momentum, and this y-axis is the energy. And this first column is obtained by the backpropagation. The first row is obtained by the backpropagation method, and this second row is obtained by strong field approximation. And the first column is for circular polarization, and the second column is for elliptical polarization. Okay, so then this construct of the same diagram at the tunnel exit is surprisingly a very sharp line distribution. This kind of very sharp distribution is not like seen every day in your life, right? Because usually it sounds you would expect some sort of broad distribution, but here there are very sharp distributions. This means there are some conservation laws present in this diagram. And now let's look at it in more details. If you can see this red dashed line, is this correlation distribution is very closely aligned to this red dashed line. And this SFA results is even exactly coincident with this red dashed line. This red dashed line can be expressed by this equation. And this equation has very clear physical meanings. Starting from this minus IP, where corresponding to this dashed line, this dotted line, for each photon absorbed, the angular momentum increased by 1, then the energy would correspondingly increase by omega. So this is really some sort of photon concept coming out. And this, if you compare the backpropagation results and the SFA results, you see that it's slightly curved, has some slight curvature, and is also have a slight downward shift. And these are both effects are because of the presence of the Coulomb potential from the parent ion. But aside from that, this really agree with this expression really well. And this is a sharp distribution. Again, it means this expression is fulfilled at all times within an optical cycle. Because if the expression for the relation for the energy and the angular momentum, if it's different at different times, then it would not give you such a sharp line. And this points to the existence of quasi-photons at the subcycle level. We can even do a time-resolved study, like this is for the circular polarization at different time instances during a sub-cycle of the optical field. We can see that the energy and angular momentum fulfill this conservation law nicely at all times. This is for circular polarization. And if we come back and look at the elliptical polarization, we see that it's no longer so sharp. It's instead a little broadened. And we can, if we look carefully more carefully from the SFA diagram, we find that the slope of this distribution changes. It changes between epsilon times omega, and this epsilon is the ellipticity of the elliptical field. It changes between epsilon omega and omega divided by epsilon. Indeed, this frequency correspond to the field peak, and at the field valley, it has this frequency. We can see it more clearly from the time-resolved study that at the field peak, this is the total field, right? At the peak of the field, this quasi-photon has an energy of epsilon times omega, while at the valley of the field, it has a frequency of omega divided by epsilon. And at any time in between, you can represent it by a time-varying angular frequency. So this points to the existence of quasi-photon at a sub-cycle level. But the good thing is that for circular polarization, the quasi-photon has the same frequencies at all times, while for the elliptical polarization, it has a different energy at different times. Now, because this is a tonal ionization, the ionization yield is maximum for the field peak. So this overall shape is more close to this epsilon times omega. But anyway, it is broadened and having a varying frequency within the optical cycle. Okay, so we can look at other differential quantities, such as the time dependence of the angular momentum, because this points to the number of quasi-photons absorbed at different times during the laser pulse. And again, this first column is for the circular polarization, and the second column is for the elliptical polarization. The first row is obtained by the backpropagation method. The second row is obtained by the SFA. And the third row is the initial transverse momentum at the tunnel exit. You can see that this black line is the average value of the angular momentum at different time instances. You can see that when the field peaks, the transferred angular momentum is indeed a minimum. And at the field valleys, the transferred angular momentum is a peak. So this time-resolved angular momentum, it oscillates inversely with the electric field. The backpropagation results agree very well with the SFA results. And now we want to understand why it behaves like this. So we have some derivation in the framework of SFA, and we can write down the angular momentum here. We can see that the angular momentum depends on the time during the laser pulse, as well as this transverse initial momentum at the tunnel exit. So it is beneficial to look at the transverse momentum. You can see that the transverse momentum follows the same trend that is minima at the field peak and maxima at the field valley. So we think of approximate this angular momentum, the average value of the angular momentum by inserting this line into this expression, and what results is this red line. And you can see that this red line agrees well with this black line. This means that the variation of the initial transverse momentum with respect to time is passed on to the transfer of angular momentum during the pulse. So this means that the non-adiabatic, and we know that the initial transverse momentum varies because of the non-adiabatic tonal effects. So this means the non-adiabatic tonal effects are passed on to the quasi-photon absorption. Up to now, we have focused on the SAME diagram for at the tonal exit. If we look at the same diagram but at asymptotic region, we found the same, very similar relation, but the relation has an additional term that you need to subtract it by the ponderomotive energy. And if you compare this relation to the well-known peaks for the ATI structure, you find that you simply substitute this LZ by the number of photons absorbed, and it's exactly the same equation. So in order to obtain such diagram, a crucial point is that we need the phase of the photoelectron momentum distribution, because this LZ, you need to, it's written as this. You really need the phase of the momentum distribution to obtain this SAME diagram. And you know, for an experiment, you cannot easily get a phase. The way to get the phase out is a typical way is to construct some interference experiment, and we can consider doing this. To do this, beforehand we present this momentum distribution here in a polar coordinate, and this is the first ATI order, second and third ATI order, and the phase distribution look like this, and we aim to retrieve such phase distribution so that we can get this SAME diagram out. And this is our retrieved phase distribution. The way to do this is to use two circular polarized counter-rotating light pulse, and this will give rise to the electron vortices. And from the vortex structure, we can retrieve the phase, and then we can construct the same diagram. And you see the same diagram looks like this now for the above threshold ionization. Because above threshold ionization have clear peaks, so it's now more discretized than the tonal ionization, which is just follows this line. And the retrieved result agree with the SFA result very well. Again, we can look at the existence of quasi-photons under a optical cycle by looking at the vortex structure from different angles. And doing this will help us to construct the same diagram at different emission angles. Again, it's exactly the same. So this again points to the existence of quasi-photon at the subcycle level. Okay, up to now, we have been giving this concept of the quasi-photon. You may ask, can it have any practical use? And we demonstrate here 3 applications of the concept of quasi-photon. The first is about an ultra short pulse. Here is a effective 1-cycle pulse. For this particular pulse shape, the vector potential is written as this, and this electric field is written as this. You can see that the electric field and the vector potential has a different angular momentum. It has different angular frequency. You may now ask, which angular frequency participant in our quantum process? And for this Fourier transform, you can clearly see that they have different frequencies. If this A field has a wavelength of 1,000 nanometers, then the electric field would have 800 nanometers wavelength. So the question is, whose frequency is seen by the quantum process? And if we construct this diagram, it is very clearly seen that the slope corresponds to 800 nanometers for that at the tunnel exit. So this means at the tunnel exit, we see the frequency of the electric field. Then this means for the quantum tunneling process, it's the electric field that participant in this quantum tunneling process. And we can also look for the clues from the transverse momentum at the tunnel exit. Again, they agree with the 800 nanometer results better. But for the asymptotic momentum, interestingly, it agrees more with the 1,000 nanometer case. So this tells us that for the 2-step tunnel ionization process, because it's composed of the 2 steps, the first step is the quantum tunneling, and the second step is the classical motion after tunnel ionization. This tells us that the quantum tunneling dynamics is dictated by the electric field, while the classical continuous motion is dictated by the vector potential. Another application is about its application to the atomic p orbitals, and this is the results for the p plus and p minus orbitals. This is again this same diagram, and this is the distribution of angular momentum, and this is the initial energy at the tunnel exit. People have usually used the SFA regime, SFA method with this saddle point equation. But with this diagram, we found that it does not give the correct same diagram. Also, it does not give the correct initial energy distribution. However, if we change this IP by an effective IP that includes the orbital, a magnetic quantum number, then the results become correct. For the asymptotic distribution, the conclusion is the same, that we need this term in the saddle point equation. We have a simple derivation here, but I think I don't have time to go through it. Another application of this of the quasi-photon concept consists of the study about the transition between multiphoton ionization and tunnel ionization. And this corresponds to the about threshold ionization. If you increase the intensity, the characteristic parameter decreases, and it becomes more and more like a straight line. Here is still sort of multi-fold ionization. I didn't put more plots here, but if you have seen this, the diagram for the tunnel ionization, you would also already see that for the tunnel limit, it's really this straight line here. So this also could give us a hint how the transition between multi-fold ionization and tunnel ionization goes on. For these three applications, yeah, it's just a brief talk. I don't have time to go in very detail in each of them. Okay, this is a summary of my talk. So we have proposed the concept of quasi-photon that is valid even down to the subcycle limit. And this is ensured by the existence of a infinite order dynamic symmetry in the circularly or elliptically polarized pulse. And this gives rise to the conservation laws between the energy and the angular momentum. And this conservation laws exist both at the tunnel exit and at a asymptotic regime. And the variation of the angular momentum is passed on by the non-adiabatic effects. And to prove the existence of the quasi-photon, we have designed a phase retrieval algorithm from using the electron vortices, and from that we can prove the existence of quasi-photons. And the SAME toolkit is very powerful. That we have shown that for ultra-short laser pulse, the quantum tunneling process is determined by the electric field, while the classical motion is determined by the vector potential. And we have also applied it to the atomic p orbitals and to study the transition between multi-fold ionization and tunnel ionization. Okay, these are the people involved in this study, and the majority of this work is carried out by the PhD student called Yongzhe Ma, and some small part is carried out by Xiaodan Mao. Okay, thank you a lot. Any questions?
Unfortunately, we will run out of time, and we don't have much time for questions, but people can write to your chat box, and you will discuss it
Sure.
with ourselves. Thank you. It's very insightful, very interesting talk, and we have to continue with our final speaker, Vasily. Okay, so Vasily, could you please start your presentation? Oh, okay, it's much better.
Okay, so is it okay now?
Yes, nearly perfect.
Okay, great. So I'm starting from the introduction, which presents some experimental results on resonant harmonic generation. In these experiments, the heating pre-pulse is focused at the solid target surface, and main generating pulse generates harmonics. I'm presenting here the results for gallium plus, and in this ion, there is a strong transition from the ground to the outer ionizing state, and the excitation energy is 21.9 eV, so it is higher than the threshold and ionization threshold. And we see that the resonant harmonic is so strong that other harmonics are hardly visible in this experimental spectrum. In the tunnel ionization regime, we can see that the enhancement is about 2 orders of magnitude. And in the multiphoton ionization regime, when we are using 400 nanometers, the enhancement is even stronger. It is.
Vasily, I'm terribly sorry to interrupt. We cannot see the whole screen of you. It's cropped. We can see only one half of the screen. You have to, yes, thank you. That's what you have to do.
Okay, thank you. Thank you very much. Okay, so this emission is nicely collimated, and it means that it is coherent. And in the multiphoton ionization regime, the enhancement factor is about 700. So unfortunately, they have not measured the absolute efficiency in these experiments, but it should be at the level of 10 to minus 4 or even higher. Also, some resonant features were observed at the in the experiments in gases. So in xenon and krypton, there is a joint resonance near 100 eV, and enhanced generation of harmonics in this spectral region was observed. In helium, opposite to this, we have very narrow outer ionizing states, and narrow features corresponding to the states were observed when they used very short generating pulse, and supercontinuum was generated. Finally, in argon, there is this window resonance near 17th harmonic, and when they used very high density of the generating target, this window resonance resulted in this very sharp XUV line. So several models were suggested to describe the resonant harmonic generation. I would like to focus at our model, where the first step and the second step is the same as in the four-step model, but when the electron comes back to the origin, it can recombine to the ground state, but also it can be captured by the parent ion, so that the whole system itself finds itself in the outer ionizing state. The state can be photoionized, it can auto-ionize, but also it can relax to the ground state emitting XUV. So all the four processes are coherent, this emission is coherent, and certainly it is effective if the energy of the returning electron is close to the energy of the outer ionizing state. Basing on this model, we have developed the well-known Levenshtein theory to describe resonant harmonic generation. Namely, on top of the ground state and free state considered in the Levenshtein theory, we consider also the outer ionizing state, which has complex energy, and the imaginary part of the energy describes the decay of the outer ionizing state. So writing down the dipole moment as function of time, we have the free ground transitions contribution, which was considered in the Levenshtein model. Also, we have this transition from outer ionizing state to the free state, which does not provide high harmonics. And the third term is the transition from the outer ionizing states to the ground state, and it provides the resonant contribution. So after some efforts, we write the spectrum emitted in the presence of the resonance as the product of the spectrum emitted in the absence of the resonances, and a factor which is unity far from the resonance and which can be much higher than unity near the resonance. This product depends on the detuning from the resonance, on the width of the resonance, and also on this capital Q, which is written as following. It depends on matrix elements of the ground state, outer ionizing state, and free states. So formally, this result is very similar to the well-known Fano equation, but the difference here is that our capital Q is essentially complex. So in the next slide, we present this resonant factor for different values of capital Q, different absolute values and different phases. Here, the absolute squared of the resonant factor is presented, and here the phase is presented. So we see that the enhancement line can be very asymmetric, and also that there is a strong phase variation near the resonance. And the slope of the phase near the resonance corresponds to the delay in the emission of the resonant harmonic. And this delay is approximately the doubled lifetime of the quasi-stable state. So this result agrees with the naive picture of the four-step model when the system stays for a while in the outer ionizing state and then emits. We compare our results with the experimental findings. First of all, we compare the width of the enhancement line with the width of the resonance, and we find that the experimental found enhancement line is somewhat wider than the width of the resonance, but this is not a surprise because the harmonic line itself has some width. Also, phases of the resonant harmonics were studied by the rabbit techniques. It was done for tin plasma, which demonstrates the enhanced generation of 17th harmonic. So we see that the emission times of the harmonics far from the resonance are similar to the prediction of the SFA, but the two side bands near the resonance are affected by the resonance, and the prediction of our theory reasonably agree with the experimental findings. Finally, I would like to say a few words about our numerical simulation of this phenomena. So in general, outer ionizing state is a multi-electron phenomenon, so it cannot be directly simulated using single active electron approximation. But the problem is that dealing with more than one electron is computerally very heavy. So one of the solutions is using some model potential which reproduces the role of the other electrons and solves this Schrödinger equation for this potential in the single active electron approximation. We're using the following model potential. This is the usual soft Coulomb potential, and this barrier which is superimposed at the Coulomb potential. In this potential, we have the ground state, several excited states, including Rydberg's, and also one quasi-stable state which models the outer ionizing state or shape resonance or whatever. Choosing the parameters of the barrier, we can, to some degree, simulate the parameters of the real transition. And here are some results. We compare the predictions of our analytical theory with the numerical simulations on the line shape and the phase near the resonance. We see that there is an agreement between analytical theory and numerical stuff. And here I would like to stress that in the analytical theory, we haven't got any influence of the laser field on the resonant transition, but certainly it is taken into account in the numerical simulations. So from here, we can conclude that at least at these parameters, the role of the effect of the laser field at the resonant transition is not very dramatic. In the introduction, I mentioned this giant resonances in xenon and krypton near 100 eV, and broad resonance potentially supports the short at a second pulse generation from the group of resonantly enhanced harmonics. So we have simulated this numerically. Here I present the emission time as a function of the photon energy. We see that this emission time agrees with the production of the simple man model, except the small region near the resonance. But this region is very important because harmonics are enhanced here by the resonance. Looking more carefully at the emission time near the resonance, we find this behavior, and this behavior can be understood as a trade-off between the well-known Atta chirp, which appears due to free motion of the electron, and the resonance-induced Atta chirp. Writing down the equations describing these Atta chirps, we can find the condition where they compensate each other. And we indeed see that in these conditions, there is a group of harmonics which have the same emission time. So they are emitted simultaneously, and one can expect the generation of the spectrally limited at a second pulse from these harmonics. Calculating the XUV intensity as a function of the time, we indeed find the short at a second pulse generated due to resonant harmonics. It is shorter, and also it is more than 10 times more intense than the harmonics, than the at a second pulse obtained using cutoff harmonics. This was the one approach for the numerical simulations, and the other one is considering two electrons, but in one-dimensional system. So such system is known as one-dimensional helium. So this is a Schrödinger equation for two electrons and the potential. It includes the interaction of the electrons with nucleus and the interaction of the two electrons with each other. Here I present the electronic density and real and imaginary part of the wave function for ground state, for the excited state, and for lowest outer ionizing state. So what is nice is that this very simple system supports outer ionizing states, and one can easily see this part of the wave function which leaks out from the central part, which is transiently bound near the origin. Here we present the energy level of this system. There are different outer ionizing states, namely the states which has the parity opposite to the parity of the ground state, and states which has the same parity. So if the state has the opposite parity with comparison to the ground one, it is called bright outer ionizing state, and if the parity is the same, it is called dark outer ionizing state, and usually they are not seen because a single photon transition is forbidden from the states to the ground state. However, if we deal with resonant harmonic generation, Such states can be seen because they are addressed by the laser field. For example, here we present the results of the simulations for the case when this state is in resonance with 14 laser quanta, and it leads to the enhanced generation of the neighboring harmonic 13 and 15. Experimentally, they observed the enhanced generation of the harmonic which is in resonance with dressed dark outer ionizing state in indium. Here are the experimental results, and one should say that this enhancement is quite pronounced. Namely, it is comparable to the enhancement of the resonance with the bright outer ionizing state, which is also present in indium plasma. Here I would like to conclude. So within the four-step model, the resonant harmonic generation can be understood as following. The electron is detached from the parent ion, accelerated by the laser field, trapped by the parent ion, and then it relaxes to the ground state emitting XUV. The funnel-like equation for the microscopic high-frequency response was found. Resonantly induced dephasing can compensate the aperture, and this harmonic synchronization allows at a second pulse shortening in conjunction with resonance-induced intensity increased by more than an order of magnitude. And finally, dark outer ionizing state dressed by a laser photon leads to high harmonic generation enhancement comparable to the one due to the bright outer ionizing state. Finally, I would like to thank my collaborators, the experimental team of François Legaret and Tsuneyuki Azaki from Quebec, Canada, and experimental team of Pascal Salir from France. And I would like to acknowledge the funding from Russian Science Foundation. And thank you for your attention.
Okay, thank you, Vasily. And now we have time for a few questions. Okay, probably I can ask you one question. It's very short. In Fano theory, the width of the resonance it can be converted very simply to the time the particle dwell in this resonance, dwelling time or time delay time. In your formulation of the resonance, can you convert your gamma to the dwelling time easily, or it's not so straightforward?
I think that this is the same gamma as in the Fano theory. So this is basically the width of the resonance, which can be measured measuring the photoionization cross section, for instance. So this is just exactly the same gamma.
Okay, thank you. Any more questions? If not, let's just thank the speaker and all the speakers for this session, which is now closed. Thank you. And Vasily, I send you a private question to your chat box. Please check it. Thank you.
Thank you.
Thank you. Bye-bye.
Bye, everybody.
Thank you.